Okay, this begins the quantitative lectures on Newton's laws. With respect to quantifying Newton's laws, the mathematical heart of motion is the second law, that is F equals ma. Now, as I briefly outlined in my qualitative lectures, the left-hand side of the expression is the vector sum of the forces that are acting upon an object. And then the vector sum of those forces adds up to some number here on the right-hand side of the expression. The number on the right-hand side of the expression is referred to as the net force. The word net in mathematical lingo means sum. However, the amount of acceleration doesn't just depend upon what this number is equal to. It, of course, depends upon the inertial mass of the object. The greater the mass of an object, the greater its tendency to remain at a constant velocity. Therefore, the harder it is to accelerate. That is what is meant by inertial mass. Now, with the first of my quantitative examples, beginning with this lecture, we're going to take a look at a situation where the right-hand side of the expression is equal to 0. If the right-hand side of the expression is equal to 0, this then means that the vector sum of the forces is equal to 0. This then means that mathematically all of the forces cancel each other out. What I want you to do at this point is I want you to pause this video, and then I want you to take a look at the picture that I've posted for you in today's folder that is called Lecture Demonstration Picture. So go ahead and take a look at that picture now. Okay, now that you've taken a look at that picture, let's go ahead and look at the example associated with that picture. I have it up here on my screen. Okay, a mass of 0.2 kilograms, that's 200 grams. That's the black object that I have hanging from the strings in the picture. A mass of 0.2 kilograms is held by the two strings as it's shown. The angles made by the strings with respect to the horizontal direction are 30 degrees and 45 degrees respectively. I've set this up such that the string on the right-hand side of the picture is at a 30-degree angle, and the one on the left-hand side is at a 45-degree angle. It says find the tension in each string. The word tension always refers to a force exerted upon an object due to a string. So that's what we're going to find here in this example. Once I run through the basic mathematics of the example, then I'll actually show you the demonstration once again, and specifically the readings of the tension that we'll be able to find with spring scales that are attached to the strings. At any rate, however, we begin by drawing a force diagram of the situation. Okay, now a force diagram of the situation is a description of all of the forces that are acting upon an object. Of course, forces are vectors. So in this case, there are three forces. We first of all, of course, have the object's weight straight downwards, mg. Okay, now the mass m is 200 grams, but we are going to work in metric SI units, so we write that as 0.2 kilograms. Okay, and then we have the tension to the right-hand side, right here. We're going to call this tension vector here T1, and then right here is the horizontal direction. With respect to the horizontal direction, this right here is a 30-degree angle. We're going to call that angle theta. Okay, and then off to the left-hand side like so. Right here is the second tension vector. We're going to call this one here T2. And then with respect here to the horizontal direction, we have this angle right here. We're going to call this angle phi. This angle is given to us as 45 degrees. Okay, so what we're asked to find here are the values of T1 and T2 in the example. And now here's how we apply F equals ma. So because there's no acceleration, the object is just sitting there at rest, the sum of the vector sum rather, of the forces has to equal to 0. It has to equal 0 in every possible direction. And the reason for that is because if it didn't equal 0 in one direction, this would then mean that the object would accelerate in that direction. However, there's no acceleration, so the forces have to cancel out in every possible direction. So what we're going to do is we're going to break up the diagram into x and y components, like so, that is horizontally and vertically. So now horizontally, we'll write F equals ma in the following manner. The sum of the forces in the x direction is equal to 0. This then means that for the tension vectors T1 and T2, I have to break them into components in the x and y direction. To some extent, I actually have already begun to do that on my diagram. So right here, for example, is T1. Here's the x component of T1, and then right here is the y component like so. Here for T2, here's the x component like so, and then here's the y component like so. So basically in the x direction, what this expression here is saying is that this component here of the tension pointing to the right-hand side has to cancel out with this component of the other tension vector pointing to the left-hand side. However, here's then how we'll write the sum of the forces on the left-hand side of the expression. We'll say that any force vector to the right is positive, and any force vector to the left is negative. So right here is a component of T1. This right here is the adjacent side of a right triangle. This right here is T1 cosine theta. Okay, and then right here is a T2 cosine phi, but it points in the opposite direction, therefore we'll make it negative. Like so. And then the sum of the forces here horizontally is equal to 0. Like so. Okay, this equation here is F equals ma. It's the sum of the forces horizontally equals the net force horizontally, which is equal to 0. And algebraically, we have here two unknowns, T1 and T2. So obviously, I need another equation. In this case, what we do is we sum up the forces now in the y direction. So then here's how we begin to write F equals ma. The sum of the forces in the y direction is equal to 0. So vertically, everything has to cancel out as well. Okay, now let's call upwards positive and downwards negative for simplicity. And then right here is a component of T1 that points upwards. So this right here is T1 sine of theta. Like so. Okay, and then we're going to add to that, also pointing upwards right here, this component of T2. This is T2 sine phi. Like so. And then minus mg, like so, downwards in the vertical direction, like so. And then the sum of the forces then is equal to 0 vertically, because once again, there's no acceleration in the vertical direction. So what I end up with here is just basically two equations and two unknowns now algebraically, and then we have to run through the math. Okay, before I do, however, this expression right here is F equals ma. It's the sum of the forces vertically equals the net force vertically, which is equal to 0. Okay, let me do a little bit of erasing here. I'm going to kind of clean up the board now with the things that I don't need. Like so. And now let's go ahead and start to run through the math. So to do so, what I'm going to do is take this expression right here and I'm going to solve it for T1. So let's take the T2 cosine phi and move it to the other side. Like so. And then divide the cosine theta to the other side to now get T1 by itself. Like so. And then we'll take that expression for T1 and then we'll plug it in here into the other equation. Okay, let me just complete this here on the bottom board. Okay, so now I have T1 sine theta. So I'm going to have T2 cosine phi divided by cosine theta times a sine theta. Okay, in just a moment I'm going to simplify the sine over cosine here as a tangent to keep things easy. And then plus T2 sine phi. And then with the expression above, let's go ahead and move the weight mg to the other side. Like so. Okay, now I'm going to do two minor steps here at once. I'm going to factor out the T2 from both terms here on the left. And I'm also going to write the sine theta over cosine theta as tangent. So if I do those couple of minor mathematical steps together, that then gives me the following. Like so. So take a look at that expression here carefully. And then to finish the algebra here, let's go ahead and divide the parentheses to the other side to now get T2 by itself. Like so. There we go. Let me clean this up a little bit. This right here is tangent theta, like so. And now let me go ahead and calculate this out. Of course, I need my calculator to do that. And my calculator, by the way, of course, is going to be in degree mode as I do this. Okay, so let me actually go ahead and do the denominator here first. I'm going to do cosine of 45 times tangent of 30 plus sine of 45. Okay, let's take the reciprocal of that. And then I'll multiply by the weight. So 0.2 times 9.8. Okay, and that comes out to be about 1.76. And then here are the units associated with forces. Recall from one of my qualitative lectures that we have right here in the numerator the weight, which is a type of force. The weight in metric SI units is equal to kilograms multiplied by meters per second squared. That then therefore is referred to as a Newton. In the denominator of the expression, we just have trig terms. Trig terms have no units associated with them because the trig terms are all just ratios. So then therefore, to make a long story short, basically what we end up with here are the units being equal to newtons. Like so, we write newtons as a capital N. Okay, now that I have this value of T2, let's then go up to here and then plug it into the expression for T1. And now let's go ahead and calculate that as well. All right, so T2 cosine phi. So I still have the value of T2 here in my calculator. multiply it by cosine of 45 degrees, and then divide by cosine of 30. And this then comes out to be about 1.43 newtons, like so, okay? Okay, then, as I begin to complete this problem here, I have the demonstration set up once again, by the way, on a table that's behind the camera. What I'm going to do is I'm going to go ahead and move my phone right now, and I'm going to then show you what the spring scales read that are attached to the strings that are attached to the object in our force diagram above. So bear with me as I move the camera here. Okay, like so. Okay, so here is the situation, and on the right-hand side here, we have the first spring scale, which is giving us then T1. T1 we calculated to be a little bit less than 1.5 newtons. Now let's go ahead and take a look at the scale here. Notice on the right-hand side that it's written in terms of newtons, and then if you take a look at the value there on the scale, it's a little bit less than 1.5 newtons. Okay, and then I have the other scale over here on the left-hand side. This then gives us the reading of T2. The value of T2 is about 1 3/4 or so newtons, roughly, as we had calculated. So if we go over to here and then we take a look at the value there on the right-hand side in terms of newtons, notice that it's somewhere between 1.5 and 2 newtons, so it's approximately what we had calculated on the board. This is assuming, of course, that this string here is perfectly at a 45-degree angle, and this string here is at a 30-degree angle. I didn't actually really bother to measure those out too carefully, just getting the values here on the scales correct, like so. Okay, let me go ahead and put my phone back, like so. Bear with me a moment here as I adjust my tripod. Okay, all right, good enough for now. Okay, and now let me do a little bit of erasing here before we complete this portion of the lecture. One thing I want you to notice is that the spring scales were attached to the strings were attached to the object, yet the spring scales gave us the reading of the tension forces that were exerted upon the object itself. How is that possible? The reason has to do with what is called a taut string. And as I describe what is meant by a taut string, we're also going to consider the string's mass to be negligible. Usually in basic examples where we idealize situations, we always assume that the objects themselves are much heavier than the strings that are involved in a specific example. So the string's mass is considered negligible. Okay, now here is a taut string like so, and then let's say that we're taking a look here at a point on the string. Okay, that point on the string, well, there are forces exerted upon it. There's a force exerted to the right-hand side like so. There's a force exerted to the left-hand side like so. Imagine, by the way, that this taut string is being pulled by me as I hold the string like this. Okay, the string is just sitting there at rest. The acceleration is equal to 0. So then, therefore, immediately, what could you say about the value of the tension here and the value of the tension here being applied to this portion here of the string? They're obviously the same. Tensions are the same. That's true for any point here within the string itself. So for this point here, the value of the tension in this direction and the value of the tension in this direction are the same, and they're the same as these values here. The reason for that is because if they weren't the same values, for example, if this tension force was bigger than this tension force, then this portion of the string would start accelerating in this direction. That's obviously not happening. To make a long story short, what this then means is that the value of the tension that is applied at all points along the string, all of those values are exactly the same. That's why ultimately we could use the spring scales attached to the string to read the values of the tension that are being applied to the object itself, even though the spring scales are not directly in contact with the object. So whenever you encounter problems involving strings and so on and so forth, the value of the tension associated with the forces applied by those strings is always the same thing. Okay, let me go ahead and conclude the portion of the lecture here at this point.